Good day, students. Today we are considering analysis of formulae in simple harmonic motion. Now you can see that we have the adjacent as our x, opposites, perpendicular line projection. This is the hypotenuse standing for amplitude. Now we are looking at SOHCAHTUA. SOHCAHTUA. The main objective of the study is to be able to derive an expression for linear acceleration. Now, how do we get linear acceleration? We're making use of x and amplitude, but these are the things given to us. The alphabet, the parameters given to us. We don't have anything given to us at the opposite. We are concentrating on these two. That's why we make use of adjacent and hypotenuse. Now, cos theta equals adjacent stand for x over hypotenuse a cross multiply, which is x equals a cos theta. Don't forget our w equals theta over t. We cross multiply theta equals wt. We replace it back into theta. X equals to a cos wt. Don't forget that we have some things you must take notes. Take notes, please. Now, when you are differentiating cos theta, you have minus sine theta, and when you are doing sine theta, you have cos theta. There's negative here, but when you are differentiating sine, there's no negative. Now, you now have to differentiate x with respect to time. This is a constant. W is not a constant. It comes to the front. Now you have the x, the t, by the x with respect to time equals a multiplied by w. This one will change to sine minus sine omega t. We have opened the brackets. Let's bring the w to the front. W minus WA. Let's bring it to the front. Minus WA. This negative comes to the front. Sine omega t. Here is linear velocity. Linear velocity. That's expression for linear velocity. Now we're going to get our acceleration. And linear velocity is rate of change of displacement with time. Because rate of change, the x over the t, rate of change of displacement with time. Rate of change of displacement with time. Now, to get our acceleration, we differentiate velocity once again. And when you are differentiating it, to get our acceleration with the v over the t. And when you are differentiating it, this w will come to the front, this sign will change to cos. Now we minus w a multiplied by w. We are differentiating with respect to time. Only this one will come to the front. W cos omega t. And after you differentiate it, a equals minus w times w minus w squared a cos omega t. Where a equals the linear acceleration. Don't forget, we are going to replace a cos omega t back. How do we replace it? Don't forget that when we are looking for cos theta here, cos theta previously adjacent over hypotenuse x, adjacent over hypotenuse a. X equals to a cos theta. equals to A cos omega t. We replace it back here. This one is now x. Now our A in acceleration equals to minus w squared x minus w squared x. From there, linear acceleration is the product of the square of the angular speed and the displacements. The negative sign is showing us that the acceleration is directed towards the middle of the vibration, center of vibration, while x is the measurement of distance outward. Now we now have another formula, which is centripetal acceleration. Centripetal acceleration A, which is equals minus v squared over r, minus v squared over r, and is equals to minus v squared over a. Please just take note of the formula very well. Now, since we have our v to be equals to minus wa, we can now make some replacements, which is a equals minus this v. It just normal shows that it's directed toward the center of the circle of the vibration. Now bring it back. We will not turn the negative. It's v is squared. You have w a squared. You are bringing this inside it, negative with the outside, over a. Now minus w squared a squared over a. A cancel a. This is equal to minus w squared a. At any instance of motion of simple pendulum, any instant of motion of simple pendulum, total energy, any instance equals to half mv squared plus mgh. These are the things that move together: kinetic potential energy. But when it becomes maximum to the extreme end, you now have half mvn squared. It's still the same thing, but you have to introduce n to show that it has reached the maximum kinetic energy, which is at the center, and also maximum potential energy equals to half equals to mgh maximum. The two of them is maximum when kinetic energy when it's at the middle, and potential energy when it's at the extreme end, when it's vibrating or when it's moving. Total energy equals to the addition of the two, which is equals to kinetic energy. It means that it has reached the maximum, the center, and also potential energy when you reach the extreme end before coming back. Now, another formula we need to know is the elastic restoring force, which is equals to minus fx. This minus negative is telling us that is directed toward the center of the motion. After it's moving, comes back to the center, moving to the other side, coming back to the center. That's restoring it back. Now, we need to know the work done. We need to know the work done in stretching the spring. We need to know the work done in stretching the spring. And the work done in stretching the spring is equal to force, average force times the distance. This average force times the distance. What is the average force of the restoring force? is what? Look, half minus half fx times y. You can make it fy or fx. Now since I'm using y, then I want to use y. Using y. Fy. So to stand this y is extension because of half minus half fy squared. This negative, we are not making use of it in the calculation. This is work done in stretching this spring. The next thing that we need to know is the maximum total energy stored in the spring. Maximum total energy. Maximum total energy stored in the spring. Half Ka squared. Half Ka squared. The maximum total energy stored in the spring. The maximum total energy stored in the spring equals half Ka squared, where K equals elastic constants. A equals amplitude of the motion. Amplitude. Now, at any stage of the oscillation, at any stage of the oscillation, I have to take note that energy equals half Ka squared equals half mv squared plus half ky squared. This is the energy stored in the spring. What is kinetic energy? And this one is potential energy. Kinetic energy, potential energy. We are familiar with potential energy to be mgh. Also, potential energy is half ky squared. When it's being stretched, is the work done is stretching the spring to a particular distance. When you stretch to a particular distance, it will give us the work done at which is being stretched to that point. That's why half ky squared is also an expression of potential energy, because the work done is stretching the spring. When you stretch the spring, you hold it at that point, the work done will remain stagnant there, except you remove it or release it. That was the work done in taking it. It's also potential energy at that point because it rests at the point where you stretch it to. Now, the energy is also equals to the addition of kinetic energy and the potential energy. And also, there's a formula for period under simple harmonic motion. T equals to 2 pi square root of L by G. This T stands for period, while L stands for length, and G equals acceleration due to gravity. That's to 9.8 meter per second squared. This is the end of our class. Next class, we're now going to some calculation under simple harmonic motion. Thanks.